Alright, so in this video we're going to review, first we're going to introduce what Navier-Stokes is, and we're going to talk about situations when you want to use it. Okay, so first let's introduce Navier-Stokes. And so the Navier-Stokes equations is a set of partial differential equations that basically express the conservation of mass and momentum for a flowing fluid. And so if you solve the Navier-Stokes equations, you actually get spatial distributions of velocity and pressure within a fluid. Because the Navier-Stokes equations are differential equations, we know that the solution to a differential equation is a function. And so when I say spatial distribution, what I mean is a function that gives you the velocity and pressure at different spatial locations and time within a fluid. And so the full equations actually make very little assumptions on the fluid. And so that includes the effects of viscosity and even compressibility in the right form. Yet because these equations are so complex and they include so many different effects within fluids, they're actually impossible to solve for arbitrary geometries and conditions. And to this day, no one's been able to solve for a general solution. And so the way that we actually use this in practice is that we often simplify the equations through assumptions and apply it to specific situations in order for us to get a solution to the equation. The other way that we can solve these is through computers, but that's way beyond the scope of this class. And so that's what the equation is. Let's take a look and see what the equations actually look like. And so this is the part when a lot of people kind of run away scared from the fluid mechanics class because it's very complex. So these equations are intimidating, I know. And so we have three very long differential equations that describe the conservation of momentum in the fluid. And so we have one for u, which is the x component of velocity, one for v, which is the y component of velocity, and one for w, which is the z component of velocity. And then we also have the continuity equation, which is conservation of mass. And so a lot of people forget about the conservation of mass equation, but that is also part of Navier-Stokes. And so please don't forget it. Okay. And so the equations that I'm showing you here are kind of a specialized version for Navier-Stokes for an incompressible fluid. But for most of the fluids that you deal with, unless you're working in aerospace, these equations are going to work just fine. And that's the one that we mostly focus on in an introductory fluids class like this one. Okay, so now let's ask, when can we use Navier-Stokes? And so, the real answer to this is actually you can technically almost use it anywhere because it's so general. The only issue is that you just won't be able to solve it unless you have very, very powerful computers. And so practically speaking, from an analytical point of view, we mostly use Navier-Stokes for situations that we can't apply some of our easier methods. And so if you can't use Bernoulli, if you can't use control volumes, then that's when you want to use Navier-Stokes. And most of the time, these are going to be cases when viscosity plays a big role in the flow, right? And so if you recall from Bernoulli, you recall from control volumes, one of the big assumptions that we made back then was that viscosity, we can ignore it. But there's a lot of situations out there where viscosity can't be ignored, and you have to resort to Navier-Stokes to solve those equations. And practically speaking, most of the time when viscosity plays a large role, this is when the flow goes through a small or narrow space. Okay, but this works out really well for us. And so when both of those things apply, we can actually apply a lot of assumptions to simplify these equations. Okay. And another reason you'd want to use Navier-Stokes, and this is kind of more from a computational point of view if you have a powerful computer, solving Navier-Stokes actually gives you a much richer, much more detailed view of what the flow looks like. And so remember, the Navier-Stokes equations are differential equations, and so when you solve them, you get actual functions, and those functions are often functions of space and time. So this is often a lot more valuable than, say, the solution to Bernoulli or the solution to control volumes, where those often only give you the fluid properties at discrete points, and may not be as useful for for certain applications. Okay, so the situations that you'll see a lot, especially in a fluids class for solving Navier-Stokes, are flows in pipes or flows in narrow channels, right? And so what these have in common is that they are very small. If you compare that to flow in like a atmospheric flow, and so viscosity is going to play a big role in these cases. Okay, and so whenever you have small narrow spaces and viscosity plays a big role, that's when you want to use Navier-Stokes.